So red-black trees allows us to take that really useful concept of the 2-3 tree, but use the binary search tree as the foundational data structure. So if you remember from the previous video, the great part about that 2-3 tree is anytime my tree goes to a 4-node situation, all I have to do is bubble up one of the values and keep bubbling it up until I get to the top. So I just kind of push it up. And if I get to the top and I end up with a 4-node situation, then I can just split it back into a traditional binary search tree. But how do we make that happen inside of a binary tree? Well, our book explains it, but I didn't love the explanation, so I want to give you my take on their explanation. So when we have this 2-node tree, this in between, what we're really saying is we have a binary search tree where there's a special relationship of this betweenness that's even though it's in a binary search tree. So our LQ relationship is really kind of like this, where Q is on top and L is to the side, or vice versa. Now, one of the rules that we're going to have in dealing with red-black trees is this idea that we want to lean left. And leaning left basically means if I have a 2-node situation, Q and L or L and Q, I want to have the left child be the lower one instead of the right child being the one. So in an LQ tree, Q's on the top and L's on the bottom. That's what we mean by lean left, essentially here. But that representation we just saw before with the 3 and the middle between actually says, okay, well, we have Q on the top, we have L on the bottom, and we could draw that another way like this. So we could draw it like this, where there could be drawn horizontally. I find this to be a little confusing because I got to remember which one is the child of which. But what this means is since we know the rule lean left, the Q is always going to be on the top and the L is going to be to the left. Now, I won't draw it this way because, as I said, I found it to be a mental shift that took me a while to get to, but it certainly makes it cleaner on the page. So now, though, we have a clear relationship that everything to the left of LQ is obviously L's left node. Everything to the right of LQ is obviously Q's right node. That's the same definition we had in the basic binary search tree. But that middle line that's coming off of the 3 tier is basically the stuff that lives off of L right node. Okay? And so that is how we make that transition from just a simple individual nodes to a 2-3 node by having this redness involved. So the redness is saying, okay, well, we have the between nodes, which is based off of this red relationship. So the only thing we change in our code, and I'm giving you this little bit of code here, is we can have this notion of redness or blackness. Now, some implementations use either a constant or an enumerated type or something like that to identify red and black. It's actually as simple as just saying a Boolean. Is it red? And if it's not red, it's black, right? The opposite of red is black, and so it's either red or it's not red. Thus, a black node. So that's the way I did my code. You can do it however you want to, but there's a certain simplicity in keeping it just as this little Boolean here. And so you do it whatever makes sense for you. If it's easier for you to see black and red on in your code, you write black and red in your code. Create constants or however you wish to do that. But for me, I was okay with this idea because mostly the algorithm just deals with this idea of things being red or not. So as we move into the algorithms of red-black trees, there's a few very simple yet intricate operations that you need to wrap your head around. So there's this idea of rotation, left or right. And this is moving our redness from the Q on the left and the R on the right to the L on the I'm sorry, the Q on the right and the L on the left to the other way around or vice versa. It's basically moving these hierarchies up and down. Is Q L's parent or is L Q's parent, if you will, in our tree? There's also this idea of flipping colors, very, very simple. And then the larger notice of balancing is how do I balance not the full tree, but just a specific node, a little subtree inside of there. So the great thing about our algorithm is we can stay recursive, and we only have to balance each subtree at a time, and then in turn we'll have the whole subtree balanced. All right, so let's talk about this idea of rotating left. So again, we said we want to value leaning left. It's just a choice. We could lean right, but the algorithm typically wants to lean left. And so what that means is we have the LQ23 node, but instead of L being the child of Q, Q is the child of L. So we're not leaning left in this scenario. And so all we really want to do here is we want to say, well, we want Q on top and L on the bottom, but we have this other little outlier, M, which is between L and Q. Okay, so not a big deal, but we know we just kind of want to flip the tree around. And maybe you can already imagine we want Q as the parent and L is that Q's left child, and then M is L's right child. But how do we do that? That's the algorithm that we need to talk about. So in this situation where we identify a subtree that has a right red node, we're going to use rotate left to fix that. And so essentially, this is what we do. And the trick behind that is I'm going to change L, the original parent's right node, to be, instead of Q, it's going to be pointing to M, because that's the in-between state, right? And then Q's left node, instead of pointing to M, is going to point to L. So to some degree, we're just changing those two little child, left and right nodes to get it the right way. But the trick on rotating left is I also then need to change the parent of L to point to Q instead. And that's where, in a basic binary tree, we were returning nodes all over the place in all the different recursive methods, even when we didn't necessarily use them at that point, because we needed that to be able to rotate. When we rotate, we need to restructure the tree. So rotating left, very, very simple algorithm. It's not easy to code. And what you probably need to do is use your print structure method that we talked about in the previous videos for binary search trees to make sure when you rotate left that you make this really simple little shift right here. And if not, everything's going to break. Common mistakes is you lose entire branches of your tree, or you basically have things end up in the wrong spot. They end up, your tree no longer has greater than or less than properly done. So again, visualize it. See if you can see this come to play. All right, so another tough situation here is when we have a leaning left two different times. And so basically what we're saying is, L and Q, using that example again, we have M in between them. And we recognize the fact, well, our tree is taller than it needs to be because M is between L and Q. I mean, we can see that obviously on the tree, but I can store that in such a way where my tree is shorter over time by using this concept of rotating right. So when we identify there's a red node to the left and another red node to the left, that my child and my grandchild are both red to the left, then I have this notion of rotating right. And so essentially, all we need to do is to change M such that the child of M becomes its original parent. Now, you might not have expected that, right? You might have said, oh, well, shouldn't we put M to the right of Q and L to the left of Q? Well, don't forget, even though I don't show it here, Q already has stuff to its right potentially. We don't know that. L might have stuff to its left or right, and M might have stuff to its right as well. So what we can do on the rotating right is leave Q's right alone. It's outside the scope of what we care about. We just care about the left nodes. But what we do know is that everything to the right of M is less than Q, so I can make the left of Q everything that was to the right of M. So M's right becomes Q's left, and M used to be Q's left, so all we have to do is return M back to the caller, trickle that back up the tree, and whoever used to be pointing to Q now points to M. But notice our tree just got shorter. So again, it's about developing this intuition for how do I make trees shorter. When I have the right-leaning reds, I want to make that go to the left. It doesn't necessarily shorten my tree at that point, but it certainly keeps it consistent. So I know where my betweens live all the time to the left. And in this case, when I end up that situation where I'm leaning to the left too much, I'm a little bit unbalanced to the left, I can kick it back down and make my tree shorter by moving to a black node on the right, but I move all the stuff that used to be to the right down below and shorten my tree and change my structure going up. So again, this is all about balancing just this little bit of a subtree there. And when I worry about balancing at the small scale, because the way the algorithm's designed, I end up balancing at the large scale as well. And the great part about the red black tree is I no longer have to, understand the whole picture. I no longer have to, count everything to the left and everything to the right and make sure it's all equal all the way through. I can just worry about this local little relationship of me to my left and right nodes and make sure that the redness and the blackness, stay true. So we're going to explore this a little bit more in the next video, but play with this idea of rotating left and rotating right and make sure you're printing it out so you can see it, not just hope that you coded the algorithms correctly.